when the TCP transmitter is in a slow start, the increment of the congestion window happens exponentially. However, there's only up to a certain point that the TCP transmitter is in the slow start phase before it goes to the other phase, which we've defined, which is the congestion avoidance. In fact, this phase continues as long as one of the following conditions happens. So in case the congestion window reaches a point where it's greater or equal to the SS threshold that we've defined, then we say that the TCP transmitter enters in congestion avoidance. The slow start happens or continues to happen until the first congestion event will happen. So in this case, we have a loss of segment and hence also the timeout that expires. Or the congestion window is greater than the receiving window. In this case, the congestion window will continue to increase, but the transmission window will be limited to the receiving window, which in this case has a lower value than the congestion window. So let's look at what happens exactly when the TCP transmitter is in the congestion control phase. The main thing that we identified when we talked about the slow phase, or the slow start phase, was how the congestion window increases. In this case, the main difference is that the rule for increasing the congestion window in congestion avoidance is that the congestion window will be incremented by a value of 1 over the congestion window for each of the acknowledgement which is received. To put simply, this increment is basically linear because for each of the received acknowledgement message, the congestion window will increment by a value of 1. So if it starts with a value of W, in the next step it will be W plus 1, in the next step it will be W plus 2, and so on. In a more formal way, we can say that if the congestion window allows the transmission of W segments, then the reception of the acknowledgement for all of these W segments will lead to an increase which is equal to 1 segment. We will see in the next slide with an example. But to simplify the way, or to understand better how the congestion window increases in a scenario of congestion avoidance, then we say that we see a linear increase in this congestion window. So let us see an example in which the congestion window is equal to 4, and we see that after each step, how does the size of the congestion window change? Basically, we start at the congestion window equal to 4 for each of the transmitted segments. There is a corresponding acknowledgement message, which is sent in this case from the receiver towards the transmitter. What happens is that in the next step, the congestion window will be equal to 5. This equal to 5 comes because we have 4 segments from the previous step, and after the reception of each of the segments, we have an increment by 1 over the congestion window. In this case, congestion window is equal to 4, so the increment for each of the received segment is 1 over 4, 1 over 4, 1 over 4, 1 over 4, which in total amounts to having a 4 plus 1 equal to 5 value of the congestion window. And in a similar fashion, in the next transmission, we will transmit 5 segments. For each of them, there is a corresponding acknowledgement message, and hence in the next step the congestion window will be equal to 6, 7, and so on. Is it possible that everything works so perfectly, or when does the change from the slow start to the congestion window actually happen? Of course, this switch between the slow start and the congestion window will heavily depend on the value of the SS threshold that we have set. So if we take an example in which the congestion window starts with a value of equal to 1, and we have set the SS threshold equal to 5, then we might see a scenario in which we start with 1, We go to 2, we go to 4, as we have previously defined, because we are still in a slow start phase. However, in a certain moment in time, when the congestion window is equal to 5, then since this value is equal to the SS threshold, then we say that the TCP transmitter has entered in a congestion avoidance state. And the fact that we still have the acknowledgement message which are being received is taken into account. However, we always take what is the value of the lower bound integer number. So in this case, we have 5 plus 3 times over 5, but this is rounded to the lower integer value, which in this case amounts to 5. So does this change anything else? The value of the congestion window changes or impacts also the transmission rate, because along the window, the transmission rate will increase with the increase of the congestion window. The transmission rate R, which is expressed in bytes per second, is the ratio between the congestion window and the round-trip time defined as RTT. As we see, we start with a certain number of segments which are being sent, and then there is a corresponding acknowledgement messages received, so the congestion window increases up to a point in which basically the transmission will become continuous, and the transmission between the sender and the receiver will be seamless, which is somehow also the main goal of using the TCP protocol. We have previously defined that the transmission window, denoted as SWND, is the minimum value between the receiving window and the congestion window. Typically, the congestion window is initialized at 1, and we want to know what happens when the congestion window and the receiving window have a relation in which the congestion window is greater than the receiving window. So here we report a simple example in which in the y-axis we show the number of segments, MSS, and on the x-axis basically we have the time dimension. We define what is the receiving window. The receiving window is the value which characterizes the receiver, and the threshold is the SS threshold that we have predefined somehow. In the beginning, since we start with a congestion window equal to 1, we are in the slow start phase. The increment, as we said, is exponential, and this exponential increase will happen up to a point when the SS threshold is equal to the congestion window. Since the SS threshold is equal to the congestion window, as of now we enter in the congestion avoidance state. From now onwards, the increase in the congestion avoidance is linear. Hence, the value of the transmission window will be 9 and 10. So it increments by 1 in a linear way. However, what happens when the value of the congestion window, or in this case the transmission window, SWND, is equal to the receiving window, equal to 10? In this case, it is limited to the value of the receiving window. This is because the transmission window depends on both the receiving window and the congestion window. So even though we are in the congestion avoidance phase, in which the congestion window itself can continue to increase linearly, so to 11, 12, 13, 14, and so on, because the value of the receiving window is fixed to 10, then the value of the transmission window will be fixed to 10, and there will be 10 segments which are continuously transmitted. This is why before we have identified the transmission as being continuous, because as of this moment there are 10 segments which are continuously transmitted between the TCP transmitter and the TCP receiver. There are different ways of handling what we have discussed until now, depending on the state in which the TCP transmitter finds itself. However, we want to know what happens if we have a congestion. So In case we have a congestion, then we might have a timeout. A timeout means that there is a segment which has been transmitted, but for which we have not received an acknowledgement. Then the window will no longer grow since I have stopped receiving acknowledgements, basically. And the SS threshold and the congestion window can be adjusted according to certain rules. So these rules as to how the SS threshold and the congestion window are adjusted are the following. So basically, we start from the assumption that a retransmission timeout expires, so there is a segment which is lost. Then the TCP will react by setting the value of the SS threshold according to a certain formula. And the formula is given here. Basically, the TCP transmitter will set the value of the SS threshold equal to the maximum between twice the number of maximum segment size and the half the value of the flight size variable. What does this flight size variable mean? Flight size basically refers only to the bytes in flight. Bytes in flight means the bytes that have been transmitted by the transmitter but have not yet been acknowledged. So the SS threshold will depend on the amount of bytes that have been transmitted but not yet acknowledgement. And typically this value is higher than 2 MSS, or as you see here, in case it's not, then the value of the SS threshold is simply set equal to 2 MSS. When this happens, when we have a scenario in which the retransmission timeout expires, then the congestion window will be set equal to 1. And this might depend on the different versions of the TCP, but that's somehow the rule according to which we usually set the congestion window. And here it's a note on what usually is the value of the bytes in flight. However, this does not necessarily have to be the case always. So if we happen to be in this scenario, then the congestion window will be smaller than the threshold, and it will return to the slow start phase. And then the first segment which is sent will be the one which will be sent is the one which the timeout has expired for. So basically, we will retransmit the segment for which the transmitter never received an acknowledgement yet. To visualize all of these steps on resetting the value of the congestion window, on resetting the value of the threshold, let us look at an illustrative example. So we see an example in which we have the value of the segment sizes on the y-axis and we have time on the x-axis. We start with a congestion window equal to 1 because that's the initial value, and we have calculated or given a value of the SS threshold. Since we are in a slow start phase in the beginning, the increment of the window, of the congestion window, is exponential. And this happens up to a point that we either meet the SS threshold or we will have a loss of a segment. For this example, we assume that we have lost a segment. Once this segment is lost, then we are basically waiting for the acknowledgement because we cannot proceed. If the segment is lost, then after the timeout value, the SS threshold value will be reset according to the rule that we just explained in the previous slide. In the next step, once we have reset the value of the SS threshold, the value of the congestion window will be set again to 1. In this case, we are again in the slow start phase. The increment of the congestion window happens in an exponential fashion up to the point that we meet the value of the SS threshold. In this point, the value of the congestion window and the SS threshold is equal. Hence, we enter in a congestion avoidance phase, and the increment of the congestion window now will be linear, as we have previously defined. During this transmission in the congestion avoidance, If it happens again that we have a loss of a segment, after the timeout for this lost segment has expired, then the value of the SS threshold will be reset again according to 2 times the value of MSS, or half of the value of the bytes in flight. In the next step again, we reset the value of the SS threshold. We start with the congestion window equal to 1, and again we are starting from the slow start phase, in which the congestion window increments exponentially until it reaches the value of the SS threshold. From then on, it increments in a linear fashion. So this example allows to see how the TCP transmitter might dynamically change the amount of the segments that it transmits depending on the state of the network, depending on whether it is in a slow start phase or in a congestion avoidance phase, and accounts also for a loss of a segment during the transmission.